Hello everyone, and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced this idea of De Morgan's laws for predicative variables, and we saw how we could actually write the equivalence between this new type of propositional variable that arose out of predicative variables and quantifiers. And we also saw how that was useful to be able to negate particular statements or propositions that we saw within logic. And in this final video, what we're going to do is we're going to introduce this idea of a restricted quantifier. And where this is going to be useful is it's going to be useful when we want to formalize particular statements that effectively, as you keep reading more along this statement, the objects within that statement get restricted more and more on the domains of which they can run over. And therefore, we need to be able to kind of find a way to formalize statements that have that form. So that leads us to our first definition, which is that of a restricted quantifier. And this is going to be a restricted quantifier for a for all statement. So we take P of x and Q of x to be predicative variables. Then the restricted quantifier of for all x restricted to P of x for the propositional variable for all x Q of x is defined in that following way. In other words, we write it as this for all x subscript P of x, Q of x, and we define it to be for all x, P of x implies Q of x. So this might seem a little tricky, a little waffly, but effectively all it's saying is if I'm given the propositional variable for all x Q of x, and I want to restrict that to the values of x that also satisfy P of x, then that is what this restricted quantifier is. And similarly, that leads us to our next definition, which is the restricted quantifier for an existential quantifier. So like before, we just take P of x and Q of x to be predicative variables. Then the restricted quantifier of there exists x restricted to this predicative variable P of x for the propositional variable exists x Q of x is given by the following, which we write as this: there exists x subscript P of x Q of x, and that now is written as exists x P of x and Q of x. So in other words, let's just say that again. We're given the propositional variable exists x Q of x, and we want to restrict that to the values of x that also satisfy P of x. And that's what we write here by this restricted quantifier. And like before, it's now useful to devise a kind of equivalence between these and the negation of these statements. So let's look at our theorem here about the negation of some of these restricted quantifiers and see what they're equivalent to. So we have P and Q as predicative variables, then the negation of for all x, this subscript P of x, Q of x, so this is our restricted quantifier of Q of x to P of x, is equivalent to there exists x P of x, and I just negate the Q of x. In other words, it just flips the universal quantifier to an existential quantifier. It doesn't change the restriction, doesn't change the P of x restriction, but it does negate the Q of x. And similarly, we can also look at the negation of the restricted quantifier for an existential statement, and that is very similar. It just flips the existential quantifier to a universal quantifier, and it also negates the Q of x term, but it does not, importantly, change the P of x term. So here I'm going to just prove the first one. I'll leave you to prove the second one as an exercise, or you could also look at it in the notes. So how are we going to go about proving this? Well, the first thing is that we can just use the theorems that we did in the previous video. So using a previous theorem, it follows that we have that this thing is a tautology. So what's this effectively saying? We've got the negation of for all x P of x Q of x. Well, we can write that because we've got our definition before of what that means. That's the negation of for all x P of x implies Q of x. And we know how to negate that by looking at our previous theorem. When we negate that, we flip the universal quantifier to an existential one, and then we just negate the whole proposition on the right. In other words, that's what we've got here. So that's there exists x, and then we negate the P of x implies Q of x. But let's look at what we want to prove here. We want to prove that that is equivalent to this existential quantifier of x restricted to P of x, not Q of x. And in order to do that, all we need to do now is we need to simply show that negation of P of x, or the negation of P implies Q, is equivalent to P and not Q. And if we can show that those two propositional variables are in fact equivalent, then we've proven our initial statement. So let's make some room here and kind of move this up and start trying to prove that statement I just said there. So we'd want to again write a truth table, and what we're trying to do here, just to reiterate, we're trying to prove that not P implies Q is equivalent to P and not Q, and if we can deduce that, then we finish that proof of that first statement. So the first thing we're going to fill out here is we're going to fill out the not Q column. We've done this a lot now. You take this column, we flip around all the truth values for the Q, we take true to false, false to true to false, and false to true. And then the next column we're going to fill out is P and not Q. So we need to look at the columns for P and the column for not Q. And recall that the AND operator, well, that's only true when both values are true. So in this case, it's going to take true and false to false, true and true to true, false and false to false, and false and true to false. Now the next column we're going to fill out is we want to fill out P implies Q. So in other words, we need to look at the columns P and Q. And we know how this goes. This goes true, false, true, and finally true. And the final column that we want to be able to remember we're trying to prove here, we're trying to show the equivalence of P and not Q, and with not P implies Q. So we just look at the column for P implies Q and we flip all the truth values. That is, we take true to false, false to true to false, and true to false again. And again, what do we do now? We just look at the columns of not P implies Q and the columns of P and not Q. We see that the truth values are identical. Therefore, these two propositional variables are equivalent. And therefore, we've proven our initial statement above. So we've proven that kind of first part of this theorem. And as I said at the beginning, I'll leave you to prove the second part of that theorem, where we're looking at the negation of existential quantifiers, or the negation of restricted existential quantifiers. So that you can do yourself as an exercise, or you can look it up in the notes. But let's see how this is going to be useful again by just finishing off with an example. So we're going to start with a particular proposition, and we're going to formalize it using these restricted quantifiers. So we have the proposition: in every country, there is a city within the country in which every resident of the city either rides a bike or drives a car, but does not take the bus. So we see how as we go along, our domains are getting restricted, right? Because we've got a country, and then the city has to be in that country, and the resident or a person has to be a resident of that particular city. So how do we start this? Well, the first thing is we want to formalize this in our kind of new language of first order logic. And once we've formalized it, we can then negate it by using all our kind of theorems and rules that we've had above. So the first thing to do is to kind of look at all the objects. What are the objects here? So we want to define our objects as X, Y, and Z, and we'll denote them by those symbols. And this has the domains of discourse of countries, cities, and people, respectively. So X is running over all countries, Y is running over all cities, and Z is running over all people. So those are our domains of discourse, and those are our objects in our statement above. And now the next thing we want to do is we want to look at what are the predicates in this particular statement. So let's start with just the predicates on the people. So we've got P of Z, Q of Z, and T of Z that I've used here. And I'm denoting those as the predicates for Z rides a bike, Z drives a car, and Z takes the bus. So here Z is running over people. So when I put in people in there, I will only get a value of true or false depending on whether or not they ride a bike or drive a car or take the bus and so forth. So that's kind of the predicates for our final statement. But we also need some additional predicates that are going to be functions of two variables now that are going to effectively be used as for our restricted quantifiers. So we're going to have two more predicates that we'll call Y is in X and Z is a resident of Y, and we'll denote that by CYX and RZY respectively. So in other words, what CYX is trying to tell us is it's trying to tell us if that city is in the country, and RZY is trying to tell us if that person is a resident of the city. So that is effectively what these things are going to do. So now we've got all our tools here. We've at least built up all our kind of pieces of this statement or proposition, and we now want to write that statement in this language of first order logic. So let's make some space and let's write that statement out now using all those pieces we just defined. So we've got here, for all X, there exists a Y restricted to C of YX. So that's effectively this statement here. We've got in every country, there is a city within the country. So that's that there exists a Y, and the C of YX is making sure that that city is in the country. We've then got in which every resident of the city, so we've got every Z, which is every person, but that person is also a resident of the city, so that's the R, either rides a bike or drives a car, so that's the P of Z or Q of Z, and does not take the bus, so that's the negation of T of Z. But now we want to negate this, so what's the negation of this particular statement? Well, to negate that, the first piece, we just flip the universal quantifier to an existential quantifier, so that's nice and easy. What do we do for the next piece? We flip the existential quantifier to a universal quantifier, but we don't negate or we don't change the restriction. We don't change this C of yx predicate. And similarly, for the Z piece, we flip the universal quantifier to an existential quantifier, but we don't change the restriction R of Z, Y. And how do we do the final piece? Well, now we just negate that whole final piece. How would we negate that? We would negate it by thinking about how we negate OR operators and operators. Well, the negation of the OR operator is the AND operator, so we flip the OR into an AND, and we negate all the statements inside there. And similarly, the AND operator flips to an OR operator, and we negate the T of Z term. So in other words, we get the negation of P of Z and the negation of Q of Z, or, and we've written here, the negation of T of Z is the same as T of Z. So in other words, we've got kind of a double negative is the same as what we initially had. And then we just want to write that back out in words now. So what does that say in words? That says that there exists a country in which every city within the country contains a resident of the city that either takes the bus or neither rides a bike nor drives a car. So let's kind of reiterate the story of what we did here. We started with this initial proposition. We kind of formalized all the pieces of it in first order logic. We wrote that statement in first order logic, and then we used all of our theorems that we've introduced now to negate that statement, then translated that statement back into words to understand how to negate it. So that is where we're going to finish now. That is all the information and all the stuff we're going to be covering in logic. So we're finished with that. And the next topic we're going to start looking at is we're going to start introducing some set theory, and we're also going to look at how to produce some actual mathematical proofs. So again, just to reiterate, look at the lecture notes that are found on the Moodle page for this week, and also attempt any of the exercises relevant to what has been covered this week within the module handbook. Thanks very much, and see you next week.